Hello, welcome everyone to this edition of IMSC 60 Colloquium series. And today it's a pleasure for us that we have Ranjan Laha with us. So Ranjan is currently working in the Center of High Energy Physics at Indian Institute of Science. Ranjan recently joined as an assistant professor, not even 2 years. So before that, he did his PhD at Ohio State University. And after his postdoctoral stints at SLAC or Stanford University, he was joined position there, and University of Mainz, and then he was a fellow at CERN, postdoctoral fellow, and then thereafter he returned back to India. So he works in very interesting topics on dark matter, its indirect detection, and many other topics in astroparticle physics, which is a very important area of research current times, because in the next generation we will have a lot of experimental efforts towards detecting such particles. And so he is working on several such topics, but today he decided to tell us more about dark matter and its indirect detection. So Ranjan, please.
Okay, good. So as phases, or actually in fact as human beings, from time eternity, we have asked a very basic question: what is the universe made up of? Right? This is big. You look up at the sky, you look everything around you, and you will ask this question: what is the universe made up of? So, for as long as human beings have existed, until say last few decades, the answer was whatever makes the things around us. All right. Turns out that you could have asked the question: is that all? Is the universe made up of things which we can see around us? And we did not have the opportunity to even answer that question. The last few decades in physics and science in general has been revolutionary in the sense that we can now answer this question: is that all? The answer is no. Right? And one thing you can do, due to remarkable measurements of the cosmic microwave background, that is basically the light that is left from Big Bang. Big Bang is the start of the universe, you can think of it that way, is to measure the energy density of the universe. And this is the pie chart of the energy density of the universe. All right? So everything that you see around you, right, everything makes up about 4.9% of the energy density of the universe. This number is known to a precision less than 1%. All right? The remaining 95% is something which we do not know anything about. All right? Something like 27% makes up dark matter. This number is known to a precision of 1%, 1.5% roughly. All right? And the remaining is something even more mysterious called dark energy, which makes up 68% of the energy density of the universe. And that is known to, again, 2% accuracy. This number is known to 2% accuracy. So these are numbers which are measured extremely accurately from cosmological observations, right? And this tells you that we only know 5% of the universe, right? The remaining 95% is completely unknown. And this is something we have only known for the last few decades. All right, this pie chart was made only in the last few decades. Like, all the human beings have been existing for a long time. So finding this missing 95%, all right, this dark matter plus dark energy, is one of the major goals of physics. All right. In this talk, as you already noticed, I'll be talking about dark matter. Okay. So I will first give you gravitational evidences for dark matter. All right. There are numerous evidences. I'll just concentrate on two of them. Okay. Then I'll talk about the relic density requirement. What does that mean? That means, how do you get this number? All right, this number, as I said, is known extremely precisely to 1% accuracy. How do you get it? Right? I'll tell you one example of how you get it, and then I'll tell you one way to answer the question: what is dark matter? All right, we know that it exists, but if you ask a very basic question, what is dark matter? What is it made up of? Right? This laptop is made up of electrons, protons, things like that. Right? So you can ask a very similar question: what is dark matter made up of? We have literally no idea. All right? Indirect detection, as I will tell you, is one way to answer that question. All right? Okay, so let's first talk about gravitational evidences for dark matter. This will be evidences, by the way, not evidence. Okay, so this is a very busy slide, all right. I intentionally made it very busy, simply to show that there are many evidences for dark matter at various length scales, and 2 of them I'll explain in some detail, the remaining I'll not explain in detail, all right, but feel free to ask questions. So this plot, this is the rotation curve of this galaxy, NGC 6503, some name of some galaxy, right. What is plotted on the x-axis is the radius, is the distance from the center of the galaxy, all right. Its units are kiloparsec. 1 parsec is 3 light years, all right. If you forget that 3, this is like 1000 light years roughly, all right. And this is circular velocity. So that means we see stars and gas in that galaxy moving around, and you measure the velocity. You can measure that, all right. You see this data. All right, this is the data, all right, and I'll explain this in some detail, so I'll just skip this. But the point is, this is an evidence of dark matter at scales of say tens of kiloparsec. Again, that means 10,000 light years, roughly, up to a factor of 3. All right. So that means if you do astrophysical observations at the scale of 10,000 light years, roughly, you need dark matter. In fact, even at smaller length scales, you do need dark matter, all right. But this is just, from this you can get at least, whenever you make astrophysical observations at the scale of say 1000 kiloparsecs, 1 kiloparsec or more, you need dark matter, 1000 light years or more, right, roughly.
Beyond 10,000 light years?
You mean beyond this? Okay, that's a great question. Good. So, turns out that this is an evidence of dark matter. This halo thing that you see, I'll explain in the next slide, is an evidence of dark matter. We do not know where it falls off. We have never seen the rotation curve, but it has to follow because that's a finite. This is basically, remember, Vc is square root of this circular velocity, standard thing, right? So it depends on the mass. So we know it should fall off. We do not know where it falls off simply because there are not enough tracers. I mean, how do we measure this? We measure this by looking at stars and gas moving around it. There are not enough stars and gas away. So that's why we do not know. So the maximum we know is that it is up to, it is up to say roughly 20-30 kiloparsec. But the dark matter halo should extend to up to 100 kiloparsec, 100 or 200 kiloparsec for an individual galaxy. All right, but the precise number we do not know, but that we know from simulations. There are various ways to find it. In fact, beyond this, yeah, I mean, there are not much mass there, and you can figure out some other things. Okay, good. So this is one proof. The second proof, which I'll go over in some detail, is this. This is bullet cluster, all right, and I'll tell you in more details what that is. Basically, what you see is 2 clusters. What are clusters? Clusters are 1000 galaxies roughly bound together, like they are gravitationally bound. They collide. And I'll show you in some of the next slides where you see that most of the mass is actually not in what we see, what we can observe electromagnetically, all right. This is not the only merging cluster that we know of. As far as I know, there are roughly 70 merging clusters. In all of them, if you do the analysis, you find that you need extra matter, right? Good. So this is evidence of dark matter at the scale of megaparsecs, 10 power 6 parsecs, all right. Let's go here. So this is from this website where basically we look at supernova 1a, right? So supernova 1a is one type of supernova. You don't need to know the details, but the thing that you need to know is that the luminosity, or in other words, the light coming out from the supernova, that class of supernova can be standardized in the sense that you can say what is the intrinsic luminosity. You can do that, right? And this is actually what gave Adam Rees, this work gave Adam Rees the Nobel Prize, right? So it's really a very difficult work, but you can do it. Using this, you can show that there is dark matter at even larger length scales than this. This is tens of kiloparsec, this is megaparsec, this tells you even hundreds of megaparsec or even more, right? Even gigaparsec. This is an artist impression of our Milky Way galaxy from the side. Suppose you went out of the Milky Way, you took a picture, this is how it will look like, all right? So this is the galactic center, this is the galactic bulge, this is the galactic disk, right? So there's a disk and there's a bulge like a ball, right? And there are all these lights that you see. Some of these lights are Milky Way satellites. That means Milky Way is a big satellite. Milky Way is a big galaxy. Around the Milky Way, there are satellite galaxies, it means small galaxies, all right, with masses less than factor of 10 or more smaller than the Milky Way. They move around the Milky Way, all right. So these galaxies move around this large Magellanic Cloud, small Magellanic Cloud, and there are other ones, all right. These are two of the massive satellites. They move around the Milky Way in order to properly account for their motion, you need dark matter around this. All right. So this is a proof of dark matter at hundreds of kiloparsec.
What is the size of those galaxies?
Which one? Oh, LMC and SMC, these are roughly factor of 10 smaller than the Milky Way in mass. So Milky Way is has a mass of roughly 10 power 12 solar mass. We know that number very well, within a factor of 2, by the way. These are 10 power 11. Large is large, small is small. So they are 10 power 11 solar mass, slightly less, something like that. And the size is probably factor of few smaller than the Milky Way.
How much is in terms of parsecs?
Parsecs. Okay, good. So the Milky Way dark matter halo, right? So you have to first ask the question is size of what? Size of what we see, baryonic disk, or size of the dark matter halo? So the size of the dark matter halo of the Milky Way is roughly 100 200 kiloparsec. The size of these guys dark matter halo will be roughly few tens of kiloparsec. That's the thing. Okay, good. So this, as I said, is the CMB. All right, so you measure the universe, the cosmic microwave background, and this you see the evidence of dark matter. This is the evidence of dark matter at gigaparsec length scales, all right, 10 power 9 parsec length scales. And finally, I mean, all of this is observations, right? Suppose you are a theorist, right? And you say, well, wait a minute. I want to theoretically find if there is dark matter or not. You can actually even do that. You can try to simulate the whole universe. There are simulations which you can run on a laptop, standard laptop. You download it and you can run it. And you can only match the observations of the universe if you have something like dark matter, right? Something like a pressureless fluid. Like in simulations, you think of dark matter as a pressureless fluid. So this is a more fancy simulation which you cannot run in your laptop. All right, this is this is from the Illustrious collaboration. So in simulation, there are many people. They make a collaboration. They run simulations in big collaborations. So the left side is a real observation. All right, in this picture, left side is a real observation from the Hubble Extreme Deep Field. Right, so there's some from the Hubble telescope. There is some observation. All right, the right side is a mock simulation. Right? If I just give you this picture, right, you could say, well, okay, this is just part of a sky, right? You can obviously do this, not just pictures. You can do this. You can you can measure many properties statistically. Like how many galaxies are there per unit mass? What are the colors of the galaxy? That means what is the luminosity of the galaxies? And various things. How many black holes are there big black holes are there in the universe? You can measure all of these things, and they do match extremely well. So this is a proof that you need dark matter, which acts as a pressureless fluid in the universe in order to reproduce the observations. All right. Now let me go to.
Can I ask you a small question?
Yes, sure.
Diversion, don't answer.
Yeah, no, I'll answer it.
Are you already ruling out the modified theory?
Good. I'll tell a point about it. Good. Just wait. I'll tell a point slightly after this thing. Not this next slide, but in a few slides. So let me talk about the first evidence, galaxy rotation curve, in some detail. Right. So this is again an artist's side view of a galaxy. All right. So you can see this is the bulge. This is galactic center. This is the bulge. This is the spiral arms. All right. So if you go out of the Milky Way, take a picture, it will look like this. How fast it rotates depends on how much stuff it is inside. Pure Newton's law. All right. And then I'll come to the question later. I'll come to that. So this is actually, we should first give credit to Vera Rubin, who actually did all of these pioneering measurements. And there is a beautiful story behind it. I mean, why was she looking here in the sky, right? Because at that point when she was doing it, all the interesting stuff in the galaxy was near galactic center, right? You see, this is again velocity, radius in kiloparsec. Every galactic center is somewhere here. She was looking here. Why? Well, the stories go that she was a young astronomer and nobody gave her time in the telescope to look here. They said, oh, okay, you look here, there's nothing interesting, you just have a look, that's it. And she had a look, and after some painstaking effort, she actually found more than what is there in the galaxy here. She found more interesting stuff. So it's a very beautiful story of Vera Rubin, how she actually discovered dark matter from basically grant rejections. Her telescope times were rejected, that's why she looked here. Right? This is actually the story. Okay, good. So let's do this. So you can plot this again, distance from the center, rotation speed. This is say the picture of some galaxy. If you take, you can do this standard Newtonian mechanics. All right. If you are outside the mass, you have this formula. This should fall off, and if you're inside it, it should be sort of stable. All right. So if you just follow the mass as if the mass is following the light, then your curve will be like this. This expected. All right. But what we see is this observed. right? And there's no light here. You can say, wait, why don't we use better telescopes? We have been doing this for last 5 decades, and we know even from other observations that it's not that there are faint stars here. There is literally something new, all right? Faint stars cannot do it, okay? So this is some explanation of it, and then you can do this thing in fancy GR language also. It actually you don't require GR, but you can still do it. It still has this same thing. You cannot explain this observation with this thing. There's no way to explain it. All right? Good. So this is a very simple example of galaxy rotation curves. People have done this for various galaxies, by the way. This is I just gave examples of 1 or 2. There are people who do this for their whole life. Right? They take various galaxies and try to figure this out, this rotation curve. These are very difficult measurements, and they find it for every galaxy you require dark matter. All right? Okay, good. Let me talk about the evidence in the second thing. This is bullet cluster. All right? So before this, we need to talk about something called gravitational lensing. This is one slide on gravitational lensing. What does it show? So you must have heard that gravity bends space and light follows that bent space. All right, this is in very simple terms. This is gravitational lensing. So the story is as follows. This is the observer, Earth. This is some distant galaxy, and suppose there is something in front of you which you cannot observe, or which you can observe. All right, because of the gravity of this object, the light from this galaxy will get bent. They will not come straight towards us, they will come bent towards us. This is called galaxy lensing, right? So you see, the light is lensed. These photons should not come towards us because they are going away, and then you lens it towards the Earth. That's lensing. All right? This is again routinely observed by astronomers and cosmologists. All right? This is a real picture, right? Where basically a galaxy is lensed and you see this thing. Basically, this is a picture of all the galaxies that's actually formed. All right? So basically, again, just think of this as optics, sort of. I mean, this light goes away, so this picture will be here. This light you just go, there will be picture here, and like this will happen. All right? And this tells you that there is definitely some mass, even if it's invisible, in front of it. Okay? And this is actually done in many galaxy clusters, and we again see that we need dark matter. All right? So what is it done? How is it done for bullet cluster? So as I said, a cluster is 1,000 galaxies bound together, roughly of the order of 1,000 galaxies. So what do galaxies have? So galaxies have stars. Stars will not collide among themselves. Why? Because stars have too much distance between them. Stars will just go through them. That's it. It has gas. Gas means diffuse material in the galaxy. That will collide because of electromagnetic interactions. All right? So in this picture, what is shown in this pink things is basically gas which have collided. Right? And it's giving out some X-ray emission. All right, there's this bullet-like structure. That's why it's called a bullet cluster, and there's giving this X-ray-like emission. All right, from this emission, you can figure out what is the mass of the gas here. You can figure this out. All right, and you can also do something else. If galaxies have, or if galaxy clusters have dark matter will just pass straight through. They will not interact with matter, and you can try to lens the material in these regions. Remember, these things have had sort of friction. They have stopped, whereas dark matter has just gone through. All right? You can lens the background galaxies, right? So these galaxies that you see are actually behind this bullet cluster. You can lens them, and you can find that they have to be lensed, all right? Because again, you can do galaxy shapes. Lensing changes the shapes, all right? There are various techniques to do it. You can find that the mass in this blue region is actually 5 times the mass in this pink region. That tells you that there is dark matter in galaxy clusters. All right, there's no other way you can reproduce this signal. All right, is this clear? Okay, let's come to the part of the question. It's actually now mentioned. So what I've been trying to tell you and convince you is that if you make gravitational and cosmological observations at all scales of the universe beyond say 1 kiloparsec, that is again 1000 light years, you need dark matter. In other words, if you do not include this extra non-interacting matter, you will not fit the observations. The observations need something, right? So this is various scales. So you can do the larger scales of CMB, structure formation, lensing, and this rotation curves and various different things. All right? And then let's come to the question. All of this I said, well, it assumes GR, it assumes Newton's gravity and things like that. And you can ask, wait a minute, why are you assuming Newton's laws of gravity and GR? Why can't you modify gravity? So that's a good path to take, except that none of the modifications of gravity have been able to reproduce these observations at all scales. I mean, most of them actually can do it very well at the galactic scales. Beyond them, they just do not work. So the way I take it, I look at this way, problem, that if you make observations, there are problems in these observations, we cannot explain it. In order to explain it, dark matter is the most economical solution. You put dark matter, problems from all scales, from galactic scales to extragalactic scales will get solved. One solution will solve everything. If you do modified gravity, it may work, but currently we have not been able to show that it has worked. So it will require, I mean, there is no single unified modified gravity theory which will solve all these problems. So the way I think of this is that, again, as I said, it is an economical solution to it. Maybe nature is even more complicated. Maybe part of it is modified gravity, part of it is dark matter and things like that. But again, that we can only find by doing these observations and trying to answer these questions. Does it answer the question?
Okay,
Yeah, okay, thanks.
Still doubt about whether modified theory cannot explain.
I think at the CMB scales, they literally cannot explain. This is, I think, almost everybody agrees. Or the way they explain it, they effectively introduce a particle, sort of. So this is almost everybody agrees with. Like all this Tevez gravity and these things, this I think everybody will agree, put it this way. But I do agree at galactic scales, MOND, so this is one of the modified Newtonian dynamics, modified gravity, works extremely well. And actually we do not know why it works so well. That's also a puzzle, but I can talk later if you're interested. Okay, good. So what do we know? So given all these observations that we have been doing for the last few decades, 50 years, we know quite a few things about dark matter. All right. The first thing we know is that the dark matter candidate has to be non-relativistic. All right. Otherwise, structure formation will go crazy, and I'll show you a picture how it will go crazy. The second thing we know, it must have weak interactions with standard model particles. Here, weak doesn't mean the four forces weak, that kind of weak. It can be that weak also, but it also means it cannot interact very strongly with known matter. Otherwise, again, observations will go crazy, completely wrong. That is something we know. And we also know that the lifetime of this dark matter candidate must be greater than the age of the universe. Why? Because we see dark matter very close to us. So that means whatever is dark matter must be existing till that time, this time. So these are the three things we know. All right. Note that all of these things are actually not equalities. We just know these are inequalities, right? For example, we know that the lifetime of the candidate must be larger than the age of the universe. But what is it equal to? We do not know. We just know it's a greater than some number, right?
Ruling out ultralight dark.
No, ultralight dark matter can be a good dark matter candidate. I'm not ruling it out. Good. So non-relativistic, if it is ultralight dark matter, it has to form in a non-thermal way, such that its momentum distribution is actually non-thermal. For example, people talk of axions, which can be as light as micro eV. That's a great dark matter candidate because it's not formed in a thermal way. All right. So I'll tell you what is the mass range of dark matter in it. But ultralight particles can also be dark matter. There's nothing wrong with it.
So when you say non-relativistic, what do you mean by that?
When I say non-relativistic, it means that currently it must be, for example, in the Milky Way, the velocity of dark matter is 10 power minus 3c. Actually, in the solar circle, more precisely, the velocity of dark matter is 10 power minus 3c. More precisely, it also means that dark matter, which is beyond the Milky Way, in the universe as a whole, they are moving extremely slowly. So if you have very light particles, I mean, they do not talk to the universe, the temperature of the universe. They are never in thermal contact, technically, with the temperature of the universe. And that's why they are non-relativistic. Right? For example, the way you're asking the question is, we know the CMB temperature, that is 3 Kelvin. You can convert that to an EV scale, that's 10 power minus 5 EV roughly. And if you take the dark matter particle as say 10 power minus 22 EV, then if there's a connection between the CMB temperature and the dark matter candidate, then obviously dark matter particle is moving at very high velocities. So that means if you take light particles, it cannot have a connection with the temperature of the universe. If you take heavy enough particle, it can have a connection with the temperature of the universe. Does it answer the question?
So essentially, level understanding, they should form some kind of a condensate.
If it is a light particle, then they will form a condensate. They may form a condensate. I mean, even there is thing, when you are assuming they are forming a condensate, you are assuming it's a boson. They can also be fermions, by the way. And then they will not form condensate. So there are some caveats, all right, and I'll be happy to talk more. Okay, good. So what do we want to know? So the first question, as we were discussing, you could have guessed, what is the mass of the dark matter candidate? We do not know the answer. Right? You can ask a very simple question, what is the mass? We do not know the answer. What is the lifetime of the dark matter candidate? Again, as I said, we know its lifetime must be greater than the age of the universe. What is the number? What is the number equal to? We do not know the answer. Okay? And thirdly, what is the interaction strength of the dark matter candidate with itself and with other standard model particles? How does it interact with other standard model particles? Remember I said it has weak interactions, right, within quotes. That means its strength is smaller than some number, but what is exactly that number? We do not know the answer. Okay? So these are three of the major questions that we are trying to answer in dark matter physics. Okay? Good. So let's proceed. So now comes to one of these questions. So you can now say that, well, the fact that we require a candidate to be dark matter, why don't we look at the standard model of particle physics, right? That means all the particles that we know of. Can any of one of those particles be dark matter? Turns out the answer is no. Right? None of the particles that we know of can be dark matter. Right? In fact, the particle which could have been dark matter is the neutrino, and that was already ruled out 2-3 decades ago. Right? So suppose this is actually a plot. Suppose you a simulation actually. Suppose you simulate the universe assuming a dark matter candidate of mass 175 eV. All right. You can show that it will actually be relativistic. Right? And you simulate the universe at various redshifts, all right, various times. So this is redshift 3, redshift 2, redshift 1. All right. So these are various times. Redshift 0 is now. Redshift 1 is roughly 2 or 3 giga years ago. Right, and these are higher and higher, larger and larger times. So, right, these are early universe. Time is going up like this. Right, you get this observation. Right, suppose you take the dark matter. Suppose you take a heavier dark matter mass, right, candidate mass, and you make it non-relativistic. This will be relativistic, as I said. This will be relativistic. If you make it non-relativistic, your structure formation happens like this. There is actually a reason. This is not. I mean, there's a physical understanding behind this simulation, and I can explain why it is. But let me just skip it now. Turns out you can take each of these slices and measure how the sky looks like. So what does this mean? This is all of these bright spots that you see in these pictures. These are centers of galaxies. All right, all of these bright yellow spots, and all of these faint things that you see, these are filaments. That means matter connecting between two galaxies, and all of these dark spots are basically empty patches. So what does this mean? That means you are counting galaxies in a volume. That's what the picture is. All right, you just take a observation volume and count how many galaxies or what types are there. You just do that. That's it. You don't do anything more fancy than that. You see, this picture looks completely different from this picture. All right, this is a simulation in 2000, by the way. Even by that time, it was already ruled out. Right, and reality actually matches this picture. Right, if you make a large enough observation, large scale observation, the reality is actually like this. So this is like gigaparsec length scales. If you observe the universe at gigaparsec length scales, something like 10 power 9 parsec length scales, the universe looks like this. It doesn't look anything like this. All right, and this is pure gravity. All right, this simulation has pure gravity, nothing else. Using this, you can show that neutrinos are ruled out as dark matter candidate. Actually, you can do even more. All right, these masses cannot be neutrino masses. More precisely, neutrinos must be much lighter. Has to be much lighter, orders of magnitude, at least 2 orders of magnitude lighter. Right? These go even crazy. These simulations. All right. In other words, this is answering one of your questions. If dark matter is light, extremely light, then dark matter cannot be in thermal contact with the universe. Right? And just to give a scale, in case people don't think of in terms of EV, so this is 175 EV. 1 GeV, that means 10 power 9 EV, is the mass of the proton. So this is roughly 10 power 7 times smaller than the mass of the proton, this particle. Right? Okay, so the universe looks like this. So this tells you that dark matter cannot be neutrinos. First of all, it cannot be. It has to be non-relativistic. This is one of the proofs that it has to be non-relativistic. Okay. Okay, good. So what is again? So what then? What again? We don't answer the question. We just ruled out neutrinos, right? We didn't answer the question. What is the dark matter candidate? Turns out that the theory predictions of what dark matter candidate can be are vast and numerous. There are many things, right? Some of the famous models are the lightest supersymmetric particle, lightest Kaluza-Klein particles, sterile neutrinos, gravitinos, axions. I mean, it just goes on and on, right? The lightest a dark matter candidate can be, is roughly 10 power minus 30 GeV. Again, 1 GeV is the mass of the proton. That means the dark matter candidate can be 30 orders of magnitude lighter than a proton. It's still allowed. Everything can be fine. A dark matter candidate can be 50 orders of magnitude heavier than the proton. Again, everything is fine. Right? Nothing, as long as you make up the things properly. Right? So you see, there is 80 orders of magnitude, right, where dark matter can be. Right? Again, as was discussed, as I said, if the dark matter becomes very light, you have to make it non-thermal. That means it cannot come in thermal contact with the universe. That means it cannot scatter with the universe's particles. Right? It cannot have the same temperature. Right? If you have this, then this whole range is allowed. All right? And so the point is to search in this whole range and figure out what is the dark matter candidate. All right? Is this clear? Okay, good. So obviously, now you see there are 80 orders of magnitude, right? So there is no one technique that can be used to detect them, right? There are numerous techniques one employs. Okay. For example, lighter mass candidates can be detected by using wave-like properties. What does this mean? If the dark matter candidate is extremely light, then its phase space density is very high. If you take a given volume, the number of particles is very high, because again, we know the dark matter density extremely well. As I said, right? In this room, we know the dark matter density within a factor of within 30% accuracy, roughly. So we know the dark matter density extremely well. So if the dark matter particle is extremely light, there will be many dark matter particles in this room, right? Then we can treat it as a wave, as a fluid, right? Whereas if the dark matter particle is very heavy, then we can treat it as a single particle moving around, right? This thing can be quantified, all right? Again, if you're interested, please ask me. I'll be happy to answer. In this talk, I'll be talking about heavy dark matter candidates. All right, dark matter candidates which have a mass greater than kilo electron volt. Okay. Now, it is certainly possible that dark matter candidate will not be detected by any of the techniques that I will discuss. Right. It's also possible that dark matter candidate will not be discussed by any of the techniques that we have thought about. So we do new techniques may be required, but it's also useful to fully utilize the current techniques, in addition to searching for new techniques to search for dark matter. Okay. Okay. So I'll show you two cartoons. So these two cartoons are very famous in the sense that how various theories of dark matter are incorporated into various other particle physics theories. All right. So this is the famous supersymmetry. Sort of, there are various models of supersymmetry, and almost all of them have dark matter candidate. Right? And that's one of the things which you try to solve. Right? It's sort of like an external input, but you try to include that. There's extra dimensions, there's little Higgs, QCD axions, and various other things. Right? And there are people here in IMS who work in many of these topics. Okay. Then this is also sort of a very nice cartoon, recently released by the Quantum magazine, which tells you all the various candidates of dark matter. As I said, the lightest particle can be as light as 10 power minus 22 eV, which is roughly 10 power minus 30 GeV, very roughly. Alright, and the heaviest particle can be roughly 30 solar mass, which is roughly 10 power 51 GeV, or even more than that. The 30 solar mass is 10 power 58 GeV, right? And there are various ways to detect it. Alright, so this thing, ultralight dark matter and axions, these are detected as waves, as I told you. Alright, and these are names of various experiments: Casper, MAGIS, ADMX, MADMAX, various experiments. Alright. Yes. The reason is as follows. Okay, let me tell you the reason. Why? Now you can ask, wait, why is this stopping at 10 power minus 22? Why not? The reason is as follows. We know the size of dwarf galaxies. Dwarf galaxies are satellite galaxies. They have a size of roughly 1 kiloparsec. All right. We know dark matter is inside those galaxies, right? Because we see observationally, we see rotation curves and we see them. Now, if at this length scale, since dark matter is localized inside that galaxy, the de Broglie wavelength of the dark matter must have a size less than the size of the galaxy. All right. De Broglie wavelength is 1 over mv. Right. We know the velocity of dark matter candidates that has to be which are moving the galaxy. That gives you a limit at m. From that we get this number 10 power minus 22 eV. right? Although technically, I mean, there are caveats in the sense that when I said all this story, I assume there is only one dark matter candidate. You could have asked who told you that there are one dark matter candidate. There are many. True. Then you can wiggle around these things. But in the most minimal scenario, this is the smallest mass a dark matter candidate can have and be the only dark matter candidate in the universe. Right? So that means if there is one kind of particle which makes up the whole of dark matter, its mass must be greater than 10 power minus 22 eV. Right? This is a very robust argument. De Broglie wavelength is smaller than the size of the galaxy because the dark matter is localized inside it. Right? Simple thing, it will give you the answer immediately. Okay, good. And then you can ask why stop at 30 solar mass? Well, the smallest galaxies that we know of are 10 power 7 solar mass. So that means that's the maximum size dark matter can have. Again, if there is one candidate which makes up the full dark matter density, right? But turns out that if you go much beyond this number, there are other problems with lensing and other things. Again, I'll be happy to discuss. And so that's why we stop at roughly few hundred solar masses. That basically sets the limit. Right? And then, as I said, anything in between can actually work. So note that the electron mass is somewhere here, the proton mass is somewhere here, the neutron mass is somewhere here, right? So everything that we know is in this range. Everything else is a free game. Okay, good. So let's talk about the relic density. All right. So the relic density means what? What is the density of dark matter in the universe? The energy density of dark matter in the universe. All right. This is a number we know extremely well. As I said, we know this number to 1% accuracy. From the recent cosmic microwave background data, we know this number. This is the thing. It's a fancy way to write it, right? Forget this thing, but this is as I said, it's a fancy way to write it. But the answer is 0.12 plus minus 0.0021, right? In dimensionless units. So you just normalize the density, all right? I'll tell you what does it mean. So this is the cosmological density. That means if you measure the dark matter density, the whole universe, you get this number in some normalized units. This is basically the roughly 1% accuracy that I was telling you about. So this number is known extremely well. In fact, this number is known so well that if you postulate any model which can reproduce the dark matter density, getting this number correct is extremely difficult. Right? Now let me show you an old plot. I have purposely chosen an old plot just to show even in 2003 this was extremely difficult. Right? And in 2003 the error bar was not 1%, it was slightly more than that. So what is being plotted? So this is some supersymmetric parameter space, all right? So some parameter on the x-axis in some particle mass, some mass in the x-axis and some mass in the y-axis. You don't need to go into the details, right? Anything that you see shaded is ruled out, right? Anything, this whole region is ruled out. I'll come to that. Let me just finish this and I'll come to that. Okay. And because this is actually this thing, all right? So this comes from the Planck satellite. The previous iteration of the Planck satellite was WMAP satellite. If you wanted that this model, this supersymmetric model, reproduces the current dark matter density, only these thin regions that you see are allowed. These thin regions are allowed. All right? Everything else is ruled out. If you want that requirement that my new physics model will have a dark matter candidate, then only this thin region is allowed. As I said, from laboratory observations, this region was ruled out, this excluded region. That means everything all in white from laboratory observations, not from cosmology or astrophysics observations, from laboratory observations, all of this white region was allowed. Once you put in the fact that you need dark matter, only this thin lines you see, only this thin line is allowed. It's a very rough way to explain this plot. All right. Now let me come to the question. So this question was asked, is this number uniform? So as I said, this number, I've written it in a dimensionless way, is the dark matter density of the whole universe. But actually the dark matter density of the whole universe is not the same. For example, the dark matter density in this room is roughly 5 orders of magnitude higher than this number. Alright? For example, the density in this room is 0.3 GeV per cubic centimeter. Right? It's a fancy way to say this. Basically, it means that if you have a dark matter candidate with a mass of 1 GeV, then in a 1 liter water bottle that you have, there are 300 dark matter candidates inside that. Right? So you see, this number and this number differ by 4 orders of magnitude. Right? That is simply because if you go inside a galaxy, the galaxy is a very non-uniform thing. The potential well deepens, and then there's a clumping of dark matter, more precisely. I mean, in more technical terms, clumping of dark matter. So if you remember, most of the universe is actually empty. So for most of the universe, this number is true. But the moment you hit a galaxy, your dark matter density increases. And I'll show you a plot very soon, which shows you how the dark matter density inside a galaxy changes with the distance. Correct. Yes. Correct. Yeah, I'll show you that. Okay, good.
What is the dark matter density close to the center of the galaxy?
Good. We don't know that answer. I'll show you a plot. There's huge uncertainty. Okay, since this question was asked, so remember, I told you this number is known from cosmological observation. That means looking at the cosmic microwave background. How do we know this number? You can ask, wait a minute, this number is known to 1% accuracy. The whole universe is known to 1% accuracy, and suddenly you say that the solar system is known to 30% accuracy. How is that possible? So this number is measured in a different way. This number is measured by basically looking at stars near the sun. How are they moving, right? So you look at stars moving. So basically, this is the galactic plane. The sun is in the galactic plane, and then there are stars which are moving like this. There are many stars which are moving like this. From the motion of these stars, you can get this number. And why is it so uncertain? Why is it uncertain to 30%? Simply because we don't know the baryonic density very well, right? And then there are other reasons. I can discuss in detail. All right. Okay, good. So I don't know how much time I have. So as I said, there are various particle physics and cosmological ways to derive the correct relic density. All right. There are both thermal and non-thermal ways to achieve the correct relic density. What does this mean? Thermal means that the dark matter particle has scattered with the matter in the universe. Non-thermal means the dark matter particle has not scattered with the matter in the universe. That's what it means, right? That means this, again, in other words, thermal means it shares the same temperature as the universe temperature. Non-thermal means it does not share the same temperature as the universe temperature. All right? I'll discuss one of these mechanisms. And in this whole talk, I'll assume there is only one candidate which makes up the whole dark matter density. All right? This is an assumption, but this is an assumption which can only be tested by doing experiments, observations, and theory. Okay, so this is one way to get the correct dark matter density, and the story is as follows. Initially, dark matter particles, and this is called the thermal relic. That means here the dark matter is produced by collisions with standard model particles. Right? There are other ways, as I said, there are other ways, they are also non-thermal relics, right? And I will not discuss that. Okay, well, how is dark matter produced? Here the story is that at the very early universe, when the universe is extremely dense, dark matter candidates, I denote this by chi, and standard model particles will collide among themselves and interconvert. Alright? As the universe cools, I assume that the dark matter candidate is heavier than some standard model candidates. Right? Standard model means all particles that we know of. So because of kinematics, since the universe has temperatures decreased, this interaction will not go both ways. This interaction will only go one way. Right? One way to look at this, let's assume that the dark matter candidate mass is 100 GeV. Alright? And the electron mass is 0.5 MeV. Right? Unless the background temperature is, unless the electron has enough energy, you will not produce 100 GeV particles. If two electrons colliding will not produce 100 GeV particles. That's just energy conservation. You have to accelerate the electrons to 100 GeV of energy to produce them, right? But once the universe cools, that means once the temperature of the universe goes less than 100 GeV, the electrons are thermal. That means electrons talk to the universe, talk to the photons of the universe. They follow the temperature of the universe. Once the temperature of the universe goes less than 100 GeV, roughly, again there's a factor of few here and there, but let's forget that. Two electrons colliding will not produce dark matter. 100 GeV dark matter particles, right? Energy conservation will not allow that. But to dark matter particles, we have 100 GeV, they can collide to produce electrons, right? So again, energy conservation allows that. So this happens. Now something funny happens, and this happens because the universe is expanding. See, in this process, there are two dark matter particles which are coming close to each other and colliding and producing some standard model particles. But the universe is expanding, right? That means two particles are trying to come close to each other. The space between them are increasing, right? So you take a sort of some elastic sheet, take two balls, let the two balls come together. If you pull the elastic sheet fast enough, the balls will not come close to each other. This is exactly what happens. At some point, there are two rates. Mathematically, there are two rates. One is the rate of this interaction. The other is the rate of expansion of the universe. Once the rate of expansion of the universe exceeds this rate, this interaction also stops. That means dark matter particles will not come close to each other to interact. right? So you can do the whole thing mathematically. This can be done in a very sophisticated way. What you get is as follows. What is plotted in this thing is the time. So this is early time of the universe. This is late time of the universe, all right? And this is the abundance. So this is the equilibrium curve. That means if you are always having this interaction, then you are following this. The number density of dark matter will follow this curve, all right? Now depending on this interaction, this cross section of two dark matter particles producing standard model particles, depending on this number, where does this interaction stops depends on that. Right, as I said, remember there's a competition between two rates. One is the rate of this interaction, two dark matter particles producing standard model particles, and the expansion of the universe. Once the expansion of the universe dominates, this interaction effectively stops, and the number density sort of technically is called freeze out. That means it stops. The number density is known. All right. So that's how you can reproduce the correct dark matter relic density. All right. This is, as I said, this is one way to do it. There are various ways to do it. And actually something funny here happens. The funny thing is as follows. As I said, you can do this calculation in great detail. You will find that the dark matter density is inversely proportional to this annihilation cross section. You can do this in more details and you get a number like this, all right? The dark matter density in these dimensionless units is this number divided by the annihilation cross section of dark matter particles annihilating to standard model particles. There is a V here, this is the velocity, relative velocity, and then you do this velocity average with these things, all right? In very simple particle physics models, this number can be written as alpha square, where alpha is a coupling constant, and the dark matter particle mass squared, m chi squared. You put these numbers, take alpha is 10 power minus 2, that's sort of like the coupling constants that we know of, all right? You make the dark matter particle mass of 300 GeV, that's sort of like a weak interaction scales. You get this cross section, which is 10 power minus 26 centimeter cube per second, which is astonishingly close to the number that you require. Yeah, but you require this number to be 0.1, right? If you put this value in, you get 0.3, right? Just one back of the envelope calculation, you suddenly get this number out. And this is a profound mystery. These numbers, I gave you these example of these numbers. These numbers are sort of weak interaction scales. All right, weak interaction is beta decay. Beta decay is weak interaction, right? These numbers are weak interaction scale numbers. How come I use these numbers and suddenly I get a number which is in cosmology? Weak interactions have nothing to do with cosmology, by the way. There's orders and orders of magnitude apart. So this is actually called the WIMP miracle, weakly interacting massive particle. How come we take numbers from particle physics, we write them in the proper units, right? I just write it in terms of units. For this you don't have to do any Feynman diagrams, nothing. By dimensional analysis you will get this thing. This is how it will work. If you just take weak interaction numbers, do a dimensional analysis, you suddenly get the correct answer. This is an absolute and astonishing thing. The question is why? We don't know the answer. All right? So this is one way, as I said, but there are also other ways to do it. So this is again a more precise way to do the whole calculation, right? And this is taken from this paper, Saikawa and Shirai. What is plotted is the dark matter mass on the x-axis, and just look at this plot. And what is the sigma v required? All right, you can to get the correct relic density. All right, you see doesn't change much depending on this x-axis changes by 8 orders of magnitude. All right, this sigma v. So whenever you are on this line, you reproduce the correct dark matter density. This changes from 5 to 2, factor of 2. Within 8 orders of magnitude, this cross section changes by a factor of 2, and yet you get the same answer. This is by doing the same calculation in a more precise way, right? This is the astonishing thing. Why does this happen? We don't know the answer, all right? And there's something which we try to find out. Okay? Oh, good. So now that I have told you, remember, this is one way to find out dark matter. I mean, how do you detect it? Again, there are various ways to detect it. I'll be talking about indirect detection. So what does indirect detection mean? Indirect detection means as follows. Suppose you draw this cartoon Feynman diagram. All right?
Detection will depend on which particle you are assuming.
Sorry?
Which particle you are assuming to be dark matter? The mass of it.
For which?
No, the mass of the dark matter will depend on the detection mechanism.
Correct. And this is actually the sort of this slide is good. So this is a cartoon Feynman diagram. All right, you don't need to know anything about Feynman diagrams to understand this cartoon. So there are two standard model particles in the asymptotic state. It can be initial state or final state, and there are two dark matter particles at the asymptotic state. It can be both initial state or final state, right? Depending on which way you look at the picture, you can detect dark matter. So let's look at what LHC does. What does LHC do? LHC tries to collide two protons and produce dark matter. So LHC, the diagram goes this way, like that means you collide two dark matter, two standard model particles, two protons, and you produce two dark matter particles, very roughly. All right. I mean, there are other signatures, but anyways, I can discuss in detail. This is how LHC works. All right, all these LHC collaborations. This is called in collided production of dark matter. There is direct detection, which I will not talk about. What does this do? In this, what we do is we keep some low energy, we keep some detector in a background free environment. We try to make the background as low as possible. So that means this SM, some standard model particle is there. We hope at some point a dark matter particle will come, will collide with the SM. So this SM will give you some signature and the dark matter will just go out invisibly. Right? So there are various detectors, right? So this is something where condensed matter is extensively used to detect dark matter. All right. So you put in a dark matter, you put in a detector, various kinds of fancy detectors. You hope at some point a dark matter will come, will collide, will hit the detector. You see some signature, ionization signature, phonon signature, and various different things, superconducting signature and things like that. You will see here, this is the final state, and then the dark matter will go away invisibly. So the time goes this way. All right. Oops. And finally, what I'll be talking about is indirect detection. What does indirect detection means? Remember, I've been telling you that there are lots of dark matter in the universe. It is possible that two dark matter particles, as I said, although remember two dark matter particles, the collision has stopped, it has actually not stopped entirely. There are some residual collisions happening, very, very few collisions. So that means two dark matter particles can collide and produce two standard model particles. So this is the diagram going this way. All right. Something else can also happen which is not given in this diagram. If the dark matter particle can decay, right, then there is one dark matter particle here and that will just decay to two standard model particles, and I'll give you an example of that. All right, this is indirect detection. When this diagram, you look at this diagram, that is initial state you have dark matter particles and final state you have standard model particles. That's indirect detection. Collider is initial state you have standard model particles, final state you have dark matter particles. And direct detection is initial state you have standard model particle and dark matter particle, final state you have standard model particle and dark matter particle. That's how it works. I'll give a brief description of this. All right. So what does indirect detection look like? So again, as I said, so what you do is you look at some astrophysical observation, astrophysical or cosmological observation. You hope that two dark matter particles will collide or a dark matter particle will decay to produce standard model particles, and you will observe that from the Earth. That's what the hope is. Alright, so you search for dark matter annihilation or decay products from various astrophysical and cosmological signatures, from cosmological observations. Okay. So more precisely, what does that mean? That means you search for various standard model particles over expected astrophysical backgrounds. Alright. So we search for various particles: photons, neutrinos, positrons, antiprotons, and various things. In cartoon way, what does this mean? What it means is this cartoon. Alright. In the x-axis, what is plotted is the energy, and y-axis is plotted is some particle flux. It can either be neutrinos or it can be photons, neutrinos, positrons, antiprotons. The astrophysical background will look like this, something like this. All right, and we hope that at some point we will see an excess of these particles due to dark matter annihilation or decay. This peak. All right. And there are reasons, there are kinematic reasons why this peak cannot be mimicked by astrophysics, almost always, but again. And to do this, we look at various objects. We look at the sun, the Milky Way, dwarf galaxy, galaxy clusters, cosmic microwave background, various different things. We just look at anything that we can observe and we try to find the signature. Alright? And as I said, there's also some spectral features. Spectral feature means this thing is called a spectral feature. The spectrum is different. The energy spectrum is different. Alright. So how does this signal look like? This signal looks like, so this is actually for neutrinos, and I'm plotting it, I'm telling you the flux of neutrinos from dark matter annihilation just because it's the simplest to do. It depends on how much sky you look at, d omega, right? It depends on some particle physics inputs. What is the annihilation cross section? What is the dark matter particle mass? And what is the neutrino spectrum from that interaction? And it depends on how much dark matter is there in your line of sight. Right? So bottom line, you don't need to go into the details of the interaction of this equation. What it depends on particle physics, which tells you what is the dark matter mass, what is the annihilation cross section, and what is the final state standard model particles. And it depends on astrophysics, that what is the density of dark matter, as was asked, in some object. Right? So you look at some object. Alright, this is your observer. You look at some object, you figure out this integral like this from here. Alright. Essentially, the same formula is applicable for gamma rays. Alright. There are important modifications again, which I cannot go into now, but I can tell you more if you're interested. And there are also other modifications required for positrons and antiprotons. Okay. So what do we look at? As I said, this is a picture. As I said, we look at everything. By the way, we look at. So this is sort of like this is the galactic center. This is how the galactic signal will look like. We look at extragalactic space. We look at dwarfs, galaxies. We look at galaxy clusters. We look at everything. Right? We look at whatever we have. We look at it, and all of these have some advantage and disadvantage. All right. For example, let me talk about two different things: the galactic center and dwarf galaxies. So galactic center is the brightest dark matter source in the universe. Sorry, in the sky. In the universe. From what we observe. Why? Because it's very close. It's a flux argument, 1/d squared. It's super close. It's very bright. But there are lots of things in the galactic center. It's very difficult to disentangle the signal from background. Right? So there's a pro, but there's a con. For dwarf galaxies are quite far away. Right? So their flux is low. But they don't have much astrophysical backgrounds. So that's an advantage. Right? So this advantage and disadvantage is there in all of these things. Right? I can go over all of this, but let me not go over. But if you're interested, please ask me. I'll be happy to talk more about all of these things. All right? And this comes to the question that was asked. What is the dark matter density in, say, a typical galaxy? This is what is plotted, is the dark matter density in the Milky Way. All right? This R is the distance from the center of the Milky Way. All right? And this is the dark matter density in GeV per cubic centimeter on the y-axis. Right? We are roughly at 8 kiloparsecs from the center of the galaxy. The sun is roughly 8 kiloparsecs from the center of the galaxy. And there we know the density very well. As I said, we know it to 20-30% accuracy. So all of this measurement should coincide here. But what is it at the center of the galaxy is something we do not know. Right? It's extremely unknown. Why? Because at the center of the galaxies, the mass budget, the amount of mass is dominated by baryons. That is dominated by standard model particles. Is not dominated by dark matter. Dark matter starts dominating only when you go, say, beyond 1 or 2 kiloparsec. That's where dark matter starts dominating. In other words, known particles are much more clumped. Dark matter is much more diffuse. It's much more spread out. Right? That's what this thing. That's why for the dark matter density is huge uncertainty. We have literally no idea. So the smallest distance from the galactic center, where we have some measurement of the dark matter density, is roughly 1 kiloparsec. So say roughly here. Good. So dwarf galaxies have a size of roughly 1 kiloparsec. So again, you have to rescale this figure. But this actually is sort of true in the sense that once you go near the center, as I said, once you go near the center of the dwarf galaxies, their center means 0.1 kiloparsec roughly. There is huge uncertainty in the cross section. The huge uncertainty in the dark matter density. Far away, this is well known. This is almost always true, and this comes simply from very standard physics. Let me tell you, since the question was, let me tell you the physics. Anything that we know, like all standard model particles, we lose energy, and we know once it loses energy, it will just clump together. Right? This is, remember, this losing energy is going around and clumping. Right? Dark matter does not lose energy. All right? Dark matter does not radiate. That means dark matter does not connect to photons directly. So dark matter cannot clump, so dark matter remains diffuse. That's what the argument is, right? I mean, that's a very simple way to understand it. You can do this thing, but all these simulations, all of these things are coming from simulations. There's some data from here onwards, by the way. From roughly 1 kiloparsec onwards, there's some data. There is actually lots of data, 1 kiloparsec. So you can do all of this simulation. That's what the simulations are doing. I mean, you can do very fancy simulation, but the point is as follows. Everything that we know, like we can see, connects to photons, and then they lose energy and they clump. Whereas dark matter does not directly connect to photons. So that's why they cannot lose energy, they just remain diffuse. Alright, so let me skip this plot, this is a bit more thing. But let me give you an example of indirect detection. Alright, so there's probably 5 minutes left, right? 5 minutes left. Yeah. So let me give you an example of one thing, and I'll tell you something which is absolutely current. 1 month earlier, what has happened in dark matter indirect detection. So let me now, I've been talking about dark matter. Let me talk about something completely different. Gamma ray astrophysics. How does the universe look in gamma rays? All right. And I'll then tell you how it connects to dark matter. This is again a field by itself. Like there are people who want to look at how the universe looks in gamma rays, and we actually don't have much idea about it, by the way. All right. So one of the experiments that I'll be talking about, there are many experiments, is called the Tibet AS gamma experiment. This is an experiment in Tibet. Air shower, the AS means air shower, gamma is photons, right? This in this Yangbajing plateau. This is how the experiment looks like. This is an observatory to observe charged cosmic rays and gamma rays, right? And I mean, ask me later how they do it, and I can discuss how they do it. So Tibet AS gamma has got some path breaking results over the last 2-3 years. So the first result that they got is that they detected the first photons with energies beyond 100 TeV from an astrophysical source. All right, just to give you a scale, 1 GeV is the mass of the proton, 1 TeV is 10 power 3 GeV. So this is 5 orders of magnitude more energetic than the proton. This is the first observation. This is published here. All right, from an astrophysical source, from some source, it actually discovered these photons. Before that. This is in 2019. Before that, we did not know how the universe looked like in 100 TeV energies. We had no idea, zero idea about it, right? In 2021, last year, they discovered sub-PeV diffuse gamma rays. I'll tell you what sub-PeV means. PeV is 10 power 6 GeV, right? Peta electron volt is 10 power 6 GeV, and sub, I'll tell you what is the energy range. I'll show you, right? Sub-PeV diffuse gamma rays from the galactic disk, all right? And I'll tell you what is diffuse gamma ray and what is galactic disk later. All right. This is also the first observation. All right. Remember, this is the observation from a single source. This is the observation. This diffuse thing is not from a source. It's from parts of the galaxy which are not in an astrophysical source. Okay. These are like 2 path-breaking results. They have got it. All of this is completely gamma ray astrophysics, right? And I'll be happy to talk more about it and later connect it to dark matter. So let me talk about this first detection of sub-PeV diffuse gamma rays from the galactic disk, right? So this is a cartoon impression of the galaxy, right? If you go again far away from the galaxy, take a side-on picture. This is the galactic center, this is the galactic bulge, this is the galactic disk. There's a thin disk and there's a thick disk, right? And there's a halo, dark matter halo around it. This disk and this bulge have lots of protons in them, all right? And the remaining thing is galaxy is sort of empty. All right. So this is a map of photons from 398 TeV to 1000 TeV. Right. 1 TeV is 1000 GeV. Right. As I said, this is sub-PeV. It's just slightly less than a PeV. 1000 TeV is 1 PeV. All right. So this is the galactic disk. This line that you see is the galactic disk. All right. This line, this thing, you plot it in fancy coordinates. It is basically this line. All right. This is a map of what the universe galaxy looks like from the Tibet AS gamma. All right. Anything that is shaded is something which Tibet AS gamma cannot observe. All right. Because, say for example, you are in Madras, Chennai, you try to observe the sky, you cannot observe the full galaxy or the full sky because at some point the Earth will stop you. The Earth will, right? You cannot observe something like this, for example. You can do this for the whole year, for many years. You will not be able to observe some part of the sky from any location of the universe, of the Earth. From Tibet, these are some locations you cannot observe, so that they just grade it out. All right. So these plus marks that you see, these red plus marks, these are directions of known galactic TeV sources. These are all measurements from other observations. Right? There are many other telescopes. They have measured TeV sources coming from these plus marks. All right? You see, most of them follow the galactic disk. By the way, this is this is gamma rays.
Known galactic sources, but not in TeV or.
No. These are in gamma rays. Everything I am talking about is gamma ray. All right. These blue solid circles that you see are arrival directions of gamma ray-like events by the Tibet AS gamma. The astonishing thing is, you see most of the blue circles follow this galactic disk, near this galactic disk. All right, And the other astonishing thing is, you see, you can do a statistical analysis. None of these blue circles coincide with these red crosses. None of them cross it. So that means something is producing photons at these energies, but not producing photons at TeV energies. When I say TeV, it means 1 to 10 TeV. That's what TeV means. Alright, as I said, this is an astonishing discovery by Tibet-Ace gamma. Right? This is a discovery which gamma ray astrophysicists have been trying to do for last 50 years, and they finally did it in 2021. Alright, good. This is the spectrum. I'm almost near the end of the talk if you're impatient. So this is the energy of photons in TeV. Alright, this is the flux of photons, right, multiplied by energy to the power 2.7, some fancy ways to do it, but this is the flux of photons. This is a galactic latitude and galactic longitude. So we basically take the galaxy, divide into latitude and longitude, just like the Earth. This is the galactic longitude, and this is the galactic latitude. Alright, when mod B includes 0, that means you are in the galactic disk. Alright, so let me tell you one thing. So in this thing, this is 0, 0. Alright, and this is sort of latitude 0. The galactic disk is latitude 0, exactly, right? But the galactic disk has some thickness, so that's why they take plus minus 5 degrees. Alright, you see there are very few data points here. More precisely, in this region, there are 3 data points from Tibet-Ace gamma. There is nothing else there. As I said, this is the first time we are seeing the Milky Way in these energies from approximately 100 TeV to 1000 TeV. 100 TeV to 1 PeV. The first time we are discovering it. These are some old data points from the same part of the sky by Argo YBJ. They are at 1 TeV. Remember I was telling you about TeV sources. This is actually not a source. This is actually a diffuse thing. I'll tell you what diffuse is in the next slide. This is actually there. And these 3 lines that you see are various different model calculations of how the diffuse gamma ray will look in the Milky Way. Right? And there's something funny here. As you see, this is the first observation, and this already rules out this model, right? This pulsar halo model. You see, this doesn't match the data set. This immediately rules out. The first observation that we do, it rules out something that was viable before that observation, right? But there are other models which are viable. Tibet-Ace gamma also looked at other part of the sky, longitude 50 to 200 and mod B between 5 degrees. They found these data points again. And in this part of the sky, there was an old experiment called Casamia, where there are some upper limits, right? They did not find photons, and they exactly found it. Again, this is some prediction. All right? As I said, this is the first ever detection of galactic sub-PeV diffuse gamma rays. What does diffuse gamma ray mean? In short, so diffuse gamma ray simply means that gamma rays do not come from an astrophysical source. Remember, I showed you that plot. None of these blue circles here correspond to any other source, any source. You can look at various catalogs, none of them correspond to it. So that tells you that this is a diffuse gamma ray. That means photons do not come from a source, right? If photons come from a source, we call it a point source. If photons do not come from a source, we call it diffuse gamma rays. Alright, so last few things. So can we do dark matter with it, right? I've been telling you about dark matter, I've been telling you about dark matter, I've been telling you about cosmic gamma rays. Can we do dark matter? And this is what we had done. This is published this year. So as I said, dark matter can actually produce gamma rays. Basically, dark matter can decay, right? I talked about annihilation and decay. Let me talk about decay. Dark matter can decay to produce various standard model particles. Whatever the standard model particles do, in the end you can get lots of photons. Right? This is a very standard thing. Right? This is the part that is unknown. Can dark matter decay? We do not know. Here I am assuming that dark matter can decay. But once you produce these standard model particles, this W, Z, quarks, all of these things, they will produce lots of photons. Alright? Now given this new observation of Tibet-Ace gamma, we can immediately do this. We can say, wait a minute, I have this plot. Right? This is what Tibet-Ace gamma has produced. Let me assume that there are photons coming from dark matter decay. Alright? We know these models existed, right? These two models, remember this space independent cosmic ray and space dependent cosmic ray. These models existed, right? In other words, we know how to produce diffuse gamma rays in the galaxy. We can add that, and then it should match this flux. Right? A simple addition, right? Photons from dark matter decay plus photons from standard astrophysics should match this. In standard astrophysics, there are various models, right? These are some fancy names. You don't have to worry about that. If you're interested, please ask me. I'll be happy to answer. But there are various models in order to reproduce these data set. Our question is, is there some signal of dark matter inside this data set? All right? We do some fancy chi-square to do these things. But the bottom line is we do not find any dark matter signal. unfortunately. So what we do is we limit the lifetime of dark matter, that how long can a dark matter particle live. What is plotted on the x-axis is the dark matter particle mass in GeV, alright. Now this is 4 times 10 power 6 to 4 times 10 power 7, an order of magnitude, and the lifetime of the dark matter particle, alright. And these are huge numbers. These are numbers orders of magnitude larger than the age of the universe. The age of the universe is roughly 10 power 17 seconds. Alright, this is 10 orders of magnitude, 11 orders of magnitude more than the age of the universe. And what we want is we want to find larger and larger lifetimes. This plot is assuming dark matter particles decays to BB bar, 2 bottom quarks. Alright, anything that is shaded is ruled out. So this is the previous constraint that we had from other observations. Right, and now what we did is we used this Tibet AS gamma constraint to find this constraint. Anything that was shaded is ruled out, right? What we said is that between this range, which is roughly a factor of 3 or 4, dark matter cannot live. If it has this lifetime in this range, and it decays to this bottom quarks. Dark matter particles cannot be there just by using this Tibet AS gamma. The first measurements we found this, right? And this at the point of our publication, this was the strongest limit in the world. All right. Now this is almost my last slide. Now just to tell you, the dark matter physics is very interesting. Our limit was strongest in the world for 1.5 years. Very recently, about a month ago, slightly more than a month ago, LASSO, which is large, this is a gamma ray telescope in China, which actually did the very same thing what we did with the Tibet AS gamma. They also looked at their data set, and they have a limit. Again, what is plotted on the x-axis is the dark matter particle mass, lifetime in seconds, and this is their limit. And this is their limit is a factor of few stronger than our limit. Right? And so this is basically last month. Right? So I started from dark matter, how dark matter was produced, and I've brought you to what is happening last month in dark matter.
So the lifetime is more than 10 power 28 seconds.
In this mass range. I mean 10 power 29, now it's almost 10 power 20, assuming this BB bar.
In which mass range?
This is 10 power 6 to 10 power 8, 9, this mass range. Good. Okay, so this I conclude. I hope I've been able to convince you. The dark matter physics is a very interesting topic of research. This uses both theoretical and experimental knowledge from astrophysics, cosmology, particle physics, nuclear physics, condensed matter, etc. The cosmological and astrophysical evidence of dark matter is conclusive. Then we need dark matter, otherwise things break down. That's it. There's no question about it. However, what is dark matter? We do not know. I only discussed indirect direction. I mean, there are various ways to detect dark matter. All right, there's not enough time. Indirect direction is a major way to discover the identity of dark matter. Although we have not yet found dark matter, yet the prospects are very bright. You saw, I mean, last year, middle of last year, we got the best limit in the world. Within 1.5 years, somebody became got a limit which is stronger than us, right? So that tells you that the things are changing very fast, and we are actually having observations which can actually maybe discover dark matter at some point, right? So stay tuned for discovery of the nature of dark matter. Thank you. Sorry, over time. That's fine.
Thanks, Ranjan, for this fascinating talk, and
Yes.
we are now open for questions.
Yes.
Hi. So you looked at the decay channel going to BB bar.
Correct.
Some other channel may give some other kind of cutoffs as well.
Yes,
right?
good.
How do we like?
This is it.
Okay.
So sorry. Okay, this is but yeah. So you can do this same thing for various channels.
I see.
All right. So depending on ZZ, WW, UU bar, SS bar, tau plus tau minus TT bar, whatever you do. I mean, unless you are going with using the Tibet AS gamma observations, unless dark matter was going to first 2 generations, so either neutrinos or muons or electrons or nu bar, we always got the best limit. We got the best limits. I mean, now I think LASSO has sort of beaten us, but that was sort of obvious because LASSO is bigger than Tibet AS gamma.
Okay.
So that was sort of the moment we knew that LASSO will beat us.
Yes.
That's all. All right.
This typically occurs in 10 power minus 22 times.
Correct. So that's why I started with the example of 10 minus 22 eV. 10 minus 22 eV, there is, I mean, we cannot, whatever, as I said, remember, I said at the beginning of one point of my talk, that there are techniques which will not be applicable to dark matter. Whatever I said is not applicable to find the lifetime of dark matter if its mass is 10 power minus 22 eV. Right. So if you want to find the lifetime of dark matter when the mass is 10 power minus 22 eV, you have to do something else. I'll be happy to chat more.
the profile which you get here,
Yes.
there is a cusp problem for all the
Correct.
casting,
Yes.
which ultralight seems to be doing better. We can statement on that.
Yes, good. So let me let me rephrase the question for others. So remember, I said that we have data from here, roughly from here, where simulations merge. Here we have no data, right? So there are something called cuspy profile when the profile goes as r power -1 or even steeper. And core is r power 0. So there's something called a core and a core versus cusp problem. The problem is basically when you do observations near the center of the galaxies, various galaxies, we do not know whether we get this or this simply because the error bars are too large. There are astrophysical ways to solve it, and there are also particle physics ways to solve it. And ultralight dark matter is one particle physics way to solve it, but there are also astrophysical ways to solve it. So I think that's the basic answer. So we do not know how it will get solved. But in principle, this ultralight dark matter is a candidate, is a particle physics way to solve this core versus cusp problem. Again, I'll be happy to chat more.
So initially you said that as the universe is expanding, these
Correct.
dark matter interaction will stop at some point.
Correct.
But then you said that for this indirect observations,
Correct.
you have these residual interactions that
Correct.
happen. What are those residual interactions?
Actually, the residual interactions are still dark matter interactions. Remember when I said this thing stops, I'm saying it at the cosmological scale. The cosmological number density of dark matter is 4 or 5 orders of magnitude smaller than the number density in the solar system. Since the number density in the solar system is 5 orders of magnitude higher, this you have to do the square, right? Because of the higher number density, this annihilation will happen. Will actually restart. But cosmologically, dark matter will not annihilate, roughly. All right? I mean, again, there are caveats. If you are interested, ask me. But that's the main point. Cosmologically, this interaction stops. Cosmologically, that means if you look at the whole universe, this interaction is not happening. But if you look at certain regions of the sky where there is lots of dark matter density, then this interaction is happening.
Also, so for
This is one way to say it, one way to explain this is basically, as cosmologically, the dark matter density is uniform, but there are pockets which are very high density. There's pockets with high density, pockets with low density, but overall it's uniform. Overall this interaction is not happening, but in high density regions, this interaction is happening. That's the way to think about this.
also these channels of decay, whether
Yes.
it goes to tau
Correct,
or
correct.
bottom to
Yes.
quarks, they depend on the mass of the particle that are decaying, right?
Yes, correct.
So for massive particle, you can have a lot of channels.
Correct.
What about these super light candidates of the particle? Do
Good.
they have same kind of modeling for them?
Yes, good. So let's say I take a dark matter particle with a mass of keV, right? Remember, dark matter is non-relativistic, so its energy is roughly keV, right? It cannot produce 2 electrons. That's it. So then the only way to detect keV dark matter in indirect direction is to look at gamma gamma. That's it, nothing else. I mean, in principle, neutrino gamma is also possible. Either gamma gamma or neutrino gamma. So yeah, so what channels I'm looking at? Remember, there was this question, why am I only looking at BB bar, anti-bottom quark? I can look at something else. That depends on what mass of dark matter particle I'm looking at. Right? I mean, light particles can also go to nu bar. The keV dark particle can also go to nu bar. Right? So yeah, so that's a purely kinematic consideration. I mean, we were at masses of 10 power 6 or 10 power 7 GeV. Everything is allowed. That's why we, as an example, I showed, for BB bar, but I later showed like all kinds of particles allowed. Right?
Okay, thank you.
Yeah, welcome.
It's not just the mass, right? It's also the coupling. I mean,
Correct.
you are maybe you have assumed that the coupling to all these particles is the same,
Correct.
roughly
Good.
of the order of the
Yes,
weak
so that part I did
coupling,
not say
right?
because that's a model dependent statement, right? So this is, so given kinematically, this thing is always allowed, by using kinematics. But if you want to think of some model, this thing may not be allowed, all right? Although at this masses, this thing will always be allowed by loop corrections, more precisely. Suppose dark matter goes to only neutrinos. You can show by loop corrections, it will also talk to BB bar. W will come in? No, actually these people have done seriously.
Sure, though, I agree, but it will be like
No. At this mass is actually super important. So this is technically what is called electroweak corrections. So that means, suppose dark matter goes to nu bar, right? You can say dm goes to nu bar and there's a W coming out. At what center of mass energy is this W coming out important? It becomes very important beyond 1 TeV. Actually,
that's true.
Yeah. So here we are at a mass where everything is allowed. Everything will happens because all.
the lighter ones.
Yes, correct. So the lighter ones, that will not happen. That's why I said kinematic. Yeah, there is some particle phase thing, but I was trying to make it more simple. In kinematics ways, that's allowed. But yes, what Professor Indumurthy said is correct. There is also a particle physics argument, depending. But if you are agnostic, so in this work, we were sort of being model independent in the sense that we don't care what model is giving it. Any model which is telling you dark matter will decay to BB bar, whatever way, will be ruled out by this observation. That's it.
Model independent to the extent of interaction strength coming also to 10 power minus 2.
No. This is nothing to do with 10 power minus 2. So if you make any dark matter model and if you couple it to BB bar, right, such that this decay is happening in this mass range, then our limits will apply immediately if the lifetime is in this range. That's what I mean.
What about the interaction strength?
Yeah, so the interaction strength will determine the lifetime, right? I mean, you can make the lifetime
constraint.
So yeah, you can make the lifetime much higher than that. I cannot constrain it. But if your lifetime is using your interaction strength, using your Lagrangian, if your lifetime is in this range, or actually in this range, right, the whole thing, it will get ruled out immediately in this mass range. So that's what I mean by model independent. It is actually model independent. This, or even this result, this Lasso result, right? So if you make any dark matter candidate which decays to BB bar in this mass range, this whole region is ruled out. That means any lifetime smaller than this is ruled out, right? It cannot be there.
9 and 7, 16, 17. So 10 power 17 is the age of the universe.
Correct. So this is 11 orders of magnitude, 11, 12 orders of
Really
magnitude.
huge, I mean, okay.
Yeah, because dark matter is hardly decaying. This is actually one of the questions. Dark matter is hardly interacting. I mean, this basically says dark matter is hardly decaying. But since, why does this work? You can say, wait a minute, how come we know the lifetime of a particle which is 11 orders of magnitude larger than the age of the universe? Well, this is just simple radioactive decay, right? 1 over tau. If you look at large number of particles, one of them can decay. That's what actually is happening here.
There was an online question by Bhattu Mukhopadhyay, and he asked, is it possible to understand the sluggishness of dark matter as due to its strong self-interaction rather than thinking in terms of its mass?
Good. So let me rephrase the question. The question is, the dark matter is sluggish, that means dark matter is non-relativistic. Can I understand due to its strong self-interaction? That means dark matter interacting with themselves. Actually, we do not have any conclusive proof that dark matter interacts with itself. We have some hints, but those are not conclusive proofs. So dark matter is non-relativistic simply because how it is produced. It's not due to its self-interaction. In fact, I showed you a picture which I did not say it because there's not enough time. I didn't want to confuse you. This is a proof that dark matter does not self-interact as much as baryons, as much as standard model particles. You see, standard model particles got clumped, got caught in the center. Dark matter particles have just zoomed past it, right? Anyway, there are two blobs of dark matter and two blobs of, and that blobs of dark matter have two smaller blobs of baryons inside them, right? The baryonic blob got caught in between and they are stuck here. The dark matter blobs just went through. So this is a proof that the self-interaction of dark matter is less than some number. Right? I mean, I can give you the number in more detail, but let's not.
From this velocity, can you say anything about the mass of the dark matter?
No. So funnily what happens is from this plot what you get is the interaction cross section, self-interaction cross section by mass. You get that number. Mass of the dark matter candidate. No.
Very light mass, 10 power minus.
Yeah, so lambda by m, that's what you
Yes. What you get is correct. I mean, you can technically correct. Yeah, you get lambda by m. You will not get what is the mass. Yes. So almost no observations can tell you what is the dark matter particle mass. Almost no astrophysical observation can tell you what is the dark matter mass. This statement is actually wrong, I'm telling you. But how is it wrong? There are ways to say it. I mean, actually, I can tell you in detail why this statement is wrong. But mostly this statement is correct. Let me put it this way.
How do we know that those blue circles, dots in that plot are not due to any of the gamma? Not this, the Tibet AS gamma.
Yes, Tibet AS gamma. Yes.
Yeah,
I'm colorblind, by the way. So now you know.
So how do we know that these are not due to some gamma ray sources?
This one. Good. So you mean this, right?
No. How do we know that the blue is from diffuse gamma ray flux?
This one, right?
Yeah.
Yes. Good. So let me rephrase the question. Suppose you see gamma rays coming towards you. How do you know it's coming from a source or it's coming from a diffuse thing, that means not coming from a source? You know it by doing further observations, right? Currently, since these data points are not coinciding with any known source, we think it's diffuse. In other words, it's very weird that a source is emitting in this energy range and not emitting in anything else. That's extremely weird, right? Put it this way. Let me explain it this way.
Okay, so no other frequency is observed.
Yes, no other frequency is observed. Let me give one line. So suppose this diffuse way to produce is this. Cosmic ray protons interacting with interstellar protons and producing pi naught. So pi naught is giving gamma gamma. The moment this happens, you'll say, wait a minute, pi plus pi minus will also get produced. They will produce electrons. Those electrons will produce, they will do synchrotron radiation. How come we don't observe that? We don't observe that, that's it. That means it's not coming from a source. Every source that you see produces all other frequencies. So these sources most probably are not producing other frequencies. So these produce, that means this is diffuse. See, what is diffuse is actually a time-dependent statement in the sense that we do more observations, sometimes we actually see a source like that, right? So currently we think these sources, that means this thing, are diffuse. So that's the current understanding, right? Sources are diffuse. And people have actually tried to look for, actually only recently, last week, IceCube tried to search for photons from, neutrinos from lasso sources. They did not find anything that produced a constraint. But yeah, that's how it
And
works.
so if I followed correctly, these blue circles are
Yes.
are observed only in the AS gamma experiment.
Correct.
Like the other experiments are insensitive to diffuse gamma ray flux, or why? Like,
So the other experiments, first of all, at this energy range, only Tibet AS gamma and lasso are working.
okay,
All right.
yeah.
And there's something else I did not say. I can say it now since you asked. Lasso has also observed these photons. All right. There is preliminary data set. Lasso is observing these photons, and they also do not find any source. So these are two completely different experiments. Lasso is much better than Tibet AS gamma, as you saw, right? Their first data set, they just beat us. Back, sorry?
Where is Lasso located?
It's in China. It's nearby. Yeah. So they also do not find anything. And you can, and there are other TeV gamma ray source. There are other TeV telescopes. All right. So there's a telescope called Hawk. They also do not find anything here. By the way, there's no source that they find here. So no other telescope is finding anything here. At other frequency, at this frequency, Lasso is also not finding it. So this is actually, there is actually a corroboration of this thing. This is not yet published. It's preliminary, but it's almost certainly they are not finding anything, any source there. So that means it must be diffuse.
Okay. Yeah.
Right.
Thank you.
I mean, you can also, by the way, in principle, it can be a source. You keep on observing it, and suddenly you see more and more photons, say, from here and not from here. And that is how you find that it is a diffuse thing. Diffuse means it's all spread out. Source means there's a bright, so you pixelate the sky, you pixel the sky, and then one pixel will have many photons, the next pixel will not have photons. Think of it that way, right? If that happens, then we know that there is a source. There's possibly sources here. Currently, we cannot say that. All right, it's a confusing situation, but that's what it is. It's as it is last year's discovery, so it can't be simple. It will be confusing.
Sorry, I need to cut this discussion, and I request you to continue it in coffee and biscuits. Yeah.
Okay.
And thanks, Ranjan, again
Thank you.
for this fascinating talk.
Thank you.
And thanks for coming.